Hello students, good evening. Welcome to Wallah. My name is 𝐂𝐿𝐴. Welcome to lecture series on theory of computation. Today is our lecture number 14. In the previous classes, we have discussed something related to context-free languages and push-down automata. And our today's session is on Turing machine. So with the previous topics, we have completed first topic and second topic of our GATE syllabus, that is finite automata and push-down automata and their corresponding languages. So before going to start this topic, Turing machine, let me discuss what we studied in our previous topics. So in the first topic, we have studied finite automata. Finite automata and its corresponding language, regular language. So in finite automata, we discussed what is deterministic finite automata. Good evening all. Welcome to Theory of Computation lecture series. So in the finite automata, we discussed what is deterministic finite automata, what is non-deterministic finite automata, what is epsilon NFA, and then what is regular expression, minimization of DFA, regular languages, properties of regular languages. These are the topics we discussed in the finite automata. Then we move to grammar. Grammar topic also we consider in the second topic. Grammar. Then push-down automata. And then context-free languages. Context-free language. So grammar, also considered as second topic. So in grammar, what we studied, types of grammars, what is regular grammar, how its rule, what is context-free grammar, what is context-sensitive grammar, what is unrestricted grammar, what is the types of these grammars, and then how to identify the derivation from a given grammar, identifying the strings from the given grammar. And then in the grammar, we can study ambiguous, unambiguous grammars. Those things actually we'll study in compilers. That is also topic of grammar. We have not studied here. I'll include that in the compiler concept. Compiler is also the second topic of compiler, syntax analysis. That is also about grammar study, right? Then we move to construction of push-down automata. One of the very important automata. We spend almost 3 lectures on this push-down automata construction. If you construct push-down automata, then identifying context-free language also becomes very easy. That is what we studied in the previous lectures. Then we constructed deterministic push-down automata, non-deterministic push-down automata, and the expressive power of these two, because expressive powers are not same in these two. Expressive power of non-deterministic automata is more than deterministic automata. What is the reason? The best example language that we studied in the previous class, that is WW power R. WW power R is a special language. For this PDA possible, push-down automata possible, but non-deterministic PDA only possible, deterministic PDA not possible. Such type of, so in the PDA, whenever you say push-down automata, in which deterministic and non-deterministic natures having different categories and their acceptance methods, acceptance by empty stack, acceptance by final state, So we constructed so many PDS. Based on this, what type of languages are context free? What type of languages are not context free? So whenever more than one comparison, violation of stack properties, all these comes under non-CFLs. So these things we studied in the previous one. Today's topic is one of the very important concept, that is Turing machine. Turing machine is powerful machine compared to finite automata and Bushdon automata. Why? Because whatever the language not accepted by finite automata, that is also accepted by Turing machine. Whatever is accepted by finite automata, also accepted by Turing machine. Whatever is not accepted by Bushdon automata, also accepted by. So finite automata, assume not accepting. If any language is not accepted by finite automata, that is accepted by Bushdon automata, Turing machine. If anything is not accepted by Bushdon automata, that is also accepted by Turing machine. That's why Turing machine is the most powerful machine compared to these two. So such type of machine we are going to study in today's session. So anyhow, it is the introduction about Turing machine. So in today's session, if you have any confusions, slowly try to understand how this Turing machine is helpful for our branch of computer science, what it is, and slowly by 1 or 2 classes you feel comfortable with the designing, where we have to focus mainly for gate point of views. Normally in your BTech level you will study the theory part related to Alan Turing and all this, but whenever you are preparing for gate exam, so the main thing is we need to focus mainly on problems, way of construction of Turing machines, whenever Turing machines are given, and identifying language from those Turing machines. So this is a place where we have to focus more, right? So let us start our today's topic, Turing machine. So if you see here, we have completed this part. Context sensitive languages, generally after studying Turing machine, studying is the best, because this comes under subcategory to this. It looks like almost Turing machine and very less important for gate examination point of view, but anyhow we'll study. So directly we are moving to this last part, recursive enumerable language and this. So our whole theory of computation subject is really on this topic, Chomsky hierarchy. So we are our plan of this gate subject is, for if you are preparing for gate exam, then your plan should be, especially for this subject theory of computation, first study regular properly, because 50% weightage, 50% of the questions most of the times will get from here, 30% in general this one, the remaining will be here. But whenever these things are mainly research areas, so we'll get good questions from this, but for if you are your aim is to crack gate, then we need to focus more on this part, and then we have to focus on this, right? So Turing machine. Before going to start this, let me give a small introduction and application of this Turing machine. What this Turing machine is? The concept of Turing machine is given by Alan Turing. He is a famous mathematician. On his name there is an award also, Turing Award, very prestigious award, right? So he introduced one mathematical model. What is total theory of computation? Theory of computations are mathematical models. They are not any practical machines are not there here. They are abstract machines. theoretical concepts. So by using this, we are going to conclude about something, right? What is the main application of this Turing machine is, every problem of real world, Turing machine is a computing model. So what type of things are solvable by computers, what type of things are not solvable by computers. So in order to decide about these computing models, the concept of Turing machine was introduced by Alan Turing, right? So initially the concept of this Turing machine was given by Alan Turing. He is a mathematician. What is the main aim of it, this Turing machine is? Yes, tell me. So we have problems of decidable, undecidable problems. We have two main problems like this. Here the thing is it every real world problem is solvable by computer? Every real world problem, is it solvable by computer? Means the answer is no. There are some problems solvable by computers. There are some problems not solvable by computers. That means we cannot write algorithm for every problem. There are so many problems for which algorithms not exist. So can you write a program for every problem? Can you write algorithm for every problem? Can we run those in our computers? We can solve. That is not the. So there are problems still, not still, after 1 lakh years also there are problems which are not solvable by computers. So those problems are called as undecidable problems. The problems for which so no algorithm here. Here algorithm exists. So there are some problems for which algorithm exists. There are some problems for which no algorithm exists. We can take examples. What are the some general examples? So you can take sorting, whatever you are studying in your algorithm. So sorting problems, merge sort, quick sort, anything. Matrix multiplication, knapsack problem, all these are solvable problems. We can write an algorithm, we can write a program that is clearly solvable. Now undecidable problems, problems for which no algorithm exists. We have ambiguity problem. And we have post correspondence problem, generally called as PCP. Post correspondence problem called as PCP. So this is the problem for which algorithm not exist. Like this, if you want to do what are the problems not solvable by computers, what are the problems solvable by computers, this whole information before the generation of computers itself, all this study is made before the invention of computers with the help of a mathematical model called as Turing machine. That is the beauty of Turing machine. So Turing machine is a mathematical model. It is a mathematical concept. By using this, what type of things are computable? what type of things are not computable? All this information we can gather. So that is the Turing machine. So whatever is not solvable by computers or not solvable by Turing machine, if any problem is not solvable by Turing machine, not solved by computers. If any problem is solvable by Turing machine, then solvable by computers. Like this. So it is a abstract computer. One model of the computer is Turing machine. So that type of Turing machine we are going to study in today's session. So not only about this decidable and undecidable. With the help of Turing machine, not only this solvable and if it is a decidable, what is the complexity? Whether it is a P problem, even the algorithm exists, whether it comes under P class or NP class or NP hard. So this whole information is also identified. This whole information also identified with the help of this concept called as Turing machine. So that is the main advantage of the Turing machine. Understood? So generally Turing machines are, these are models, computing machines possibilities. In order to identify its possibilities, we are constructing Turing machines, right? So let us see mathematical model. I am saying how this model looks like. We have seen the diagram of finite automata, how it will work. We have seen the diagram of push-down automata, how it will work. Similarly, now we need to construct it. What is the aim of this session is, our aim is to learn the topic, to crack GATE exam, to solve the questions of GATE exam. For this, main thing is not much theory is not required here. So problem solving on Turing machines, how to construct a Turing machine, how to identify language, what are the properties of Turing machine, these things we have to study. This is a block diagram of the Turing machine. It looks like our previous machines, like finite automata, like push-down automata, but stacks are not there here. But not exactly same, there is a variation here, right? So look at this. Turing machine is a mathematical model that represents general purpose computer. Hence the Turing machines are used to study the power of the computer. The problem not solved by Turing machine, then this is then not solvable by computer also. This is the statement. So this thing we already studied here, right? Now come to this. If you observe this machine, this is the Turing machine model. This is the Turing machine. If you observe this, Turing machine is almost looks like our finite automata, but not exactly same. There are different capabilities are there. It looks like our automata, finite automata, but it is having so many powerful capabilities. If it is same as finite automata, how it is more powerful than finite automata? There are additional information here. Let us try it. But the structure is like this. We have an input tape. So in Turing machine, we have an input tape. So here we are reading the symbols. One side it is closed. We will read the symbols from left to right. One side closed, other side infinite. This is infinite. The other part of this will be infinite. One side closed, other side is infinite. And we have states here. Finite control is states. So from this state, we read symbols. Read the symbols and do some things. What are those? We'll see. Don't think it is a finite automata kind of thing. It is looking like that, but it is having so many powerful capabilities compared to the finite automata. What are this? So compared to finite automata, push down automata, Turing machine having additional properties. They are, first one is infinite length tape. Second one is turnaround capability. Read rate capability. So Turing machine is very powerful machine compared to your finite automata, push down automata. Where the power actually present is in the Turing machine in its inbuilt capabilities. Those are, one is infinite length tape, turnaround capability, read rate. Let me explain one by one. Infinite length tape. Before going to start designing of the machine, we'll design machines now. Before going to start that, we should know the internal structure of the machine properly. Right. So what are the capabilities? Infinite length tape. Tape length is infinite. It is, so all these remaining, your input is ended here. Input is ended here. All the remaining places are blanks. That is the structure of the Turing machine. Then turnaround capability. Second one is turnaround capability. What is this? If you observe finite automata reading from left to right only. Left to right reading only. Observe push down automata. Push down automata also left to right reading only. It cannot move back. Finite automata, push down automata, one side reading only. Once it reaches here, it will not go back. That capability is not there, but that is there in the Turing machine. So once if you come here, again it can move back. Once you come here, again it can move back. So this structure is called as a turnaround capability. So Turing machine capable to move left as well as right side direction. It can come right side, it can move left side. So these left and right movements are there in the Turing machine, but this is not allowed in finite automata and push down automata. Those things are not allowable there. Right. Next one is read write capability. So now whenever we are constructing, we'll observe all these things now. So try to understand this, how these things are happening. I'll show through examples, but these are the properties or capabilities of the Turing machine. Right. Now here, read write capability. So what finite automata and push down automata is doing is, it read the symbol A and move back, move forward. Read symbol A, move forward. Read the symbol, move forward. That's all. But Turing machine, it will read A, it can able to replace it by X. Reading symbol, replace it by some other symbol. Read write capability. Read symbol, write it by some other symbol or same symbol, anything. So this is called as read write capability. Reading A, replace it by X. It is not compulsory. You can replace it by same symbol also, not an issue. You can replace the same also. Read B, replace it by Y. Read B, replace it by Y. Read blank, replace it by X. Like this. So reading symbol can be replaced by same symbol or some other symbol. This is very, very, very powerful capability. This is the main capability. Because of these capabilities, Turing machine can accept A power n, B power n. This language. So see here, we don't have stack. We don't have a stack like push down automata, but it will accept this. And Turing machine can accept A power n, B power n, C power n. don't have stack, but it will accept this. Turing machine can accept a power n, b power n, c power n, d power n. So even though we don't have a stack, just with the help of these three capabilities, read write capability, turnaround capability, and infinite length tape, Turing machine is all this. One comparison, multiple comparison, so many comparisons. Whatever may be the number of comparisons, Turing machine can easily handle this. But finite automata fails here only. Push-down automata fails here. But Turing machine will accept all this. Along with this, Turing machine capable to accept a power n, b power m also. It can accept a power n, b power m also. Because whatever is accepted by finite automata, also accepted by Turing machine. Whatever is accepted by push-down automata, accepted by Turing machine. And whatever is not by those two, also accepted by Turing machine. So these are the, so these three things are not very easy taking things. They are very, very powerful things. Because of these things only, Turing machine can handle the languages, can accept the languages, even though it is having multiple comparisons. 3 comparison, 4 comparison, any comparison, it will handle very easily. So we'll see how, by using these capabilities, how the strings of multiple comparison will be recognized in the coming session. So this is about the capabilities of the Turing machine. Even though it looks like very simple, very, very powerful. Here also, to represent Turing machine, we have transition diagram method, transitions method. Any of this is suitable. Then Turing machine types. How many types of finite automata we have? The types of finite automata we have is 2 types. Turing machine has recognizer like DFA and FA. Turing machine has output generator, that is Mealy machine, Moore machine. How many types of push-down automata? Push-down automata having only one type in its nature, recognizer. Turing machine is 3 types. First one is recognizer. What recognizer will do? Like our finite automata, push-down automata, it will take the input. Input is accepted or rejected. Say yes or no. Your input is valid input or invalid input. Second one is output generator. Takes the input, produce the output. This is similar to Mealy-Moore machines. Third type is not exist in finite automata and push-down automata. Language generator, also called as enumerator. So what this enumerator generally do is, without having input, here in language recognizer we need inputs, output generator we need inputs, but here in the generator we don't take inputs. Without inputs, keep on produces the output. The output can be language or strings. So these type of things are called as enumerator. Anyhow, we'll construct these 3. So whenever we are studying Turing machine, practicing construction of these 3 varieties is required. It is important. So how to construct a recognizer, how to construct a generator, how to construct a language generator. Right. Now let us see the formal definition. Now we want to construct the Turing machine. So to construct the Turing machine, what we have to include in that, what should not be included. Turing machine is a 7-tuple one. So 7 tuple like this. So whenever we are constructing this Turing machine, these 7 things should be there in your machine. So like this formal in theory of computation, it's a mathematical model. So in every part of the machine, like DFA case, we studied what is the formal definition, NFA case, formal definition, every case, push down automata formal definition like this. Turing machine is a 7 tuple one. So if you want to say any machine is a valid Turing machine, 7 things should be there. Finite number of states. First Q. Input alphabet, sigma. Q0. Initial state. One initial state. F. Set of final states. B. Blank symbol. Blank symbol. Tau is tape alphabet. Then delta, transition function. The transition function of Turing machine is, see here, let us try to understand this. There are some confusions may be there. Set up till this, okay. What is a blank symbol? After your input, whatever the infinite length tape is there, all those things are placed by blank symbol. Right. Then tape alphabet. So Turing machine, what is the difference between tape alphabet and input alphabet here? Is there any difference? Tape alphabet and input alphabet. Look at this example. I am giving A's and B's as input. A's and B's as input, and there are some blanks here. This is the in the tape. Here input alphabet is symbols allowed into the input tape, that is A's and B's. So our sigma is nothing but A comma B. Sigma is A comma B. Then tape alphabet is, will perform read write capability here. Read A, replace it by X. Read B, replace it by Y. Like this, read write capability whenever you perform. Finally, this is the total tape, no? Total number of symbols allowed into tape. That is tape alphabet. So what are the total symbols in the tape now? So tape alphabet is nothing but A here, B here, X, Y, blank. So all this together is called as a tape alphabet. Total number of symbols allowed into the tape. Understood? So this is the tape alphabet. So we have read write capability. Based on that, we are replacing by some other symbols. So finally, total number of symbols allowed into the tape is tape alphabet, right? So that is about the transition function, complete information. One more thing is transition function. Total transitions, all these formal, in the formal definition, only leftover thing is transition function. Transition function is the important one. Turing machine let me write. Turing machine takes decision like this. Q cross tau gives. This is important. So whenever you want to construct the machine, what is our state? What is our present state? What is our present reading symbol? Your present state, present reading symbol. From this, your going state, a replacement symbol, moving direction. So our present state is nothing but Q. Present reading symbol tau. From this state, this input, going state is Q. Replacement symbol. So this is state, present state, and we are not considering as input alphabet, tape alphabet, because replacement symbol also we have to read. So whenever you are writing Turing machine transitions, this is the way. Our state, reading symbol. Left hand side 2 things, right hand side 3 things. Your moving thing, going state, replacement symbol. Turing machine having read replacement capability, read write capability. So replace it by Y. Then Turing machine having turnaround capability. So it can capable to move turn left as well as right side direction. So left or right, anything like this. That's why whenever we are constructing Turing machine, this is the way we have to produce transitions. Left side 2 things. What are these 2 things? What is your present state? What is your reading symbol from the tape, not from the input only, from the tape alphabet. So Q cross tau gives going state, replacement symbol, moving direction. So generally where students will generally confuse is to habituate this notation, it takes time. So it takes some time. For 1 or 2 examples you will feel comfortable. By that time if you will confuse, but nothing is there here. So if you habituate this one, if we are familiar with this, then our construction becomes very easy. We can construct Turing machines for the given questions very easily. So here in the formal definition, one of the main important thing is this transition function. Transition function. Right. So that's all about our introduction regarding the Turing machine. Now let us go and try to construct the machines. Before that, let us see once again what we studied in the Turing machine in today's session. First one is Turing machine is a mathematical model that represents general purpose computer. What a computer can do, what a computer cannot do, those things we'll study mathematically through some mathematical tools, that is Turing machine. If the problem is solvable by computer or not, we don't give it to the computer, we give to the Turing machine. Based on that we will conclude. That is nothing but mainly Turing machines are used in order to conclude about decidable problems. The problem is solvable or not by computer. The problem is that's why every year GATE paper will have a question on decidability and decidability. This topic is related to Turing machine only. So what type of problems are decidable? What type of problems are not decidable? Where algorithm exist? Where algorithm exist? Where algorithm not exist? And what type of problems are P problems, P class problems, NP class problems, NP hard problems. We have NP complete as well, NP complete. So all this classification about the problems will be done the help of Turing machine. And then we studied formal definition. What is the formal definition of the Turing machine? So looking like finite automata, but 3 important capabilities are there. So infinite length tape, turnaround capability, read write capability. Formal definition. Types of Turing machine. Okay. Now let us start construction of Turing machines. We'll move to the Turing machine construction. That is the main important one. So that will start from the language recognizer onwards. We'll try to construct, because designing is an important thing for whenever we are preparing for examination point of view. Designing of these 3 type of machines, how to design a recognizer, how to design a enumerator, how to design a output generator. These three very important. So let us start this one from recognizer onwards. Turing machine having one important property. We have to keep this in a recognizer as a language recognizer. By reading the input string, Turing machine may halt, may not halt, may go to loop, infinite loop. This is the very important property of the Turing machine. So in the construction time, we have to identify for the given language, the Turing machine can be able to construct a Turing machine which is able to halt or not. Here is the major difference between finite automata and Turing machines. Finite automata always halt for all strings. Push down automata also always halts for all strings. But Turing machine may halt for some strings, may halt for some languages, may not halt for some languages. May not halt means is may go to infinite loop. It can capable to move to infinite loop. So whether our language comes under that category or not. If it is comes under that category, loop, possible to loop, then we'll classify the language also two categories: recursive languages, recursive enumerable languages. All this classification is coming based on the nature of this type of Turing machine. That's why whenever we are constructing Turing machine, our main important thing is whether can be able to construct a halting machine or not. Halt means stop, because every machine will not stop here. Every Turing machine will not stop. Some machines will keep on fall into infinite loops, that will not come further out of that. So for those type of machines, we will conclude in a different way. So this is one, right. So acceptance is if the machine is halts non-final state, then the strings are rejected. If the machine is halt in, we're reading string, if the machine is halting in the enters into infinite loop, then we don't know. We don't know anything about the input. Don't know about the input. Whether it is accepted, or we cannot say anything about whether it is accepted or not, because it is keep on in the infinite loop, right? So these are the things. So anyhow, let us start construction of the machine for some example languages. Let me give one language. A power n, b power n, n greater than or equal to 1. So construct Turing machine for given language, for this language. A power n, b power n such that n greater than or equal to 1. We can construct push down automata, but we cannot construct finite automata. Here comparison is there. So let us try to identify the way of construction of Turing machine for this. PDA possible anyhow, but comparisons are there here. So how this comparison will be? Here we are in the basic structure of the Turing machine, we are not identifying any of the stack. Stack is not there. So without stack, how this comparison will be handled by this machine, Turing machine? Let us try to understand that one. See, first thing is logic is important, same as push down automata way. however we constructed push down automata, the way of construction of Turing machine also same. First understand the logic, identify the logic. In whatever way you identified the logic, same logic implement by transitions or transition diagram, that becomes Turing machine. So however we think about the strings, in order to accept these type of strings, what is the method you are implementing, what is the logic you are implementing? Same logic represent by show by transition diagram, that is your Turing machine, right? So here number of A's and number of B's should be equal. I'm explaining the logic, try to understand the logic first. So whatever the logic is there, that logic I'll show by transition diagram notation, that becomes our valid Turing machine. In order to check number of A's and number of B's are equal or not with our availability, so my logic is, this is there in the input, this is our input tape. Try to let me write here otherwise. Turing machine starts reading from left part of this, from left, starting from left. After that, turnaround capability, right? The logic is, whenever you are reading A, replace it by X. I think this symbol, this, replace it by X. Turing machine, whenever it reads A, it will replace it by some other symbol X. What does it mean is, there is one A. The logic is, there is one A. Then after that A comes, replace it by same, A comes, replace it by same, until B comes, because for one A, one B is required. So until B comes, move the same. Whenever B comes, replace this by Y. Replace this by Y. So whenever A comes, replace it by X. Remaining all will be same. Whenever B comes, replace it by Y. Once you replace, what is the indication here? For one A, one B is there. One A is there, for which I identified one B. Then again come back. Then Turing machine start moving left side. It will move left here. Move left. Read A, replace by same. And then read A, replace by same. Move until wherever X you find. Wherever you find X, until that will move. Whenever there is X, then start moving right side. Start moving right side. Do this process repeatedly. So let me repeat this step once again. Whatever we studied now, let me repeat this. Somewhat logical, this one. Go deep and try to understand. Turing machine constructions are like this. We'll get some beautiful questions, very somewhat complicated, we can say, some complicated questions in the gate paper. To solve this, these are basic things you need to understand. So whenever A is there, replace it by X. Then all the A's, read and replace same. Read and replace same until B encounters. Whenever there is a B, replace it by Y. Replace it by Y. Now start moving left side. Start moving left side. Move left until X. Whenever there is X, replace it by X. Start moving right side. Do the same process. Same thing here. A comes, replace it by X. After that, until B, every symbol read and replace by same. A read and replace by same, Y read and replace by same whenever B comes. What is required for me? There is one A, I made it as X. For this A, one B is required. So I am searching for B. The machine searches for B. So whenever there is a B, replace it by Y. Then start moving left side. Then start moving left side. So move left side. Whenever we are moving left side, we have to reach until X. Till that part, any Y's replace as it is, any A's replace as it is. X comes, do the same process once again. A comes, X. Till B, same. B comes, Y. Move left until X. After this X, we are searching for A. If you encounter Y, then strings are over, we have to accept. So this is the logic. This is the actual logic. Now what I will do is, for the same logic, I will explain the logic parallelly and I will construct the machine as well. I will do both, because if you just understand the logic, it seems to be confusing for you. Parallelly, I will construct the machine also, then you can understand in a better way. Start from the initial state. I am explaining the logic here. Whenever A comes, this is our Q0. Whenever A comes, replace it by X. Whenever A comes, replace it by X, move right side. A, replace it by X, move right side. Come to the Q1 state. Then what we need to do? Until B, all the A, replace it by A, replace it by A. Replace it by A, move right side. A comes, replace it by X, move right side. After that, all number of A, replace it by A, move right side. Then B, whenever B comes, replace it by Y. Same logic, see, I am not doing anything new here. Whatever the logic is there, represent the logic by diagram. So B comes, replace it by Y, move left side. See, the transitions are straight input, going straight, replacement symbol, moving direction. So the transitions look something different compared to finite automata and pushdown automata, but this is the based on transitions notation of transition function of the formal definition. Whenever there is a B, replace it by Y, move left side. Whenever there is a B, replace it by Y, move left side. So while moving left side, all number of A's, replace it by A, move left till X. So what we have to do, same thing till X. Whenever there is a X here, replace it by X, move right side. So A is there, I made it as X, skip all this. B, make it as Y, move left, skip all this. Whenever X, replace it by X, start moving right. Now we are here. Concept is same. A, replace it by X. This is already there. Now we are in Q1. So from Q1 what we need to do? Till B comes. Any number of A's replace same, any number of Y's also replace same. So that transition we need to add here. So whenever Y, replace it by Y, move right. So I think this is not required, so I am going to remove this spot. It will be confusing for you. So at Q1 state, there are two transitions. These are the Q1 state, the self loops are just bypass things. Read and replace the same things. That's why whenever we are moving right side, A's we need to replace same, move right side. Y's we need to replace same thing, because our aim is, our search is for B. So till B comes, all possibilities, replace the same, move right side. Whenever we get B, replace it by Y, start moving left side. So here nothing is difficult here. Everything is based on our formal definition or logic. So Solomon, somebody asking, if I start from now, I get a top 100 rank, is possible or not? Definitely possible. Definitely possible. So start from now, plan properly, schedule your preparation of the subjects properly, practice is a major thing. So if you practice, it's very easy. Not top 100, top 10 also it is easy. This is the right time actually. So just now GATE exam is completed and results came out. This is actually right time to start your GATE preparation. Where I get motivation? So come and join my classes. I'll motivate you every day. So this is our aim here. We are training students. So you have to keep your motivation levels as it is every day. That is also our responsibility in addition to teaching. Because once you are always motivated, then only it is easy to crack GATE exam. Every day you have to read so many hours, right? That is possible whenever you are already motivated. The problem is after 1 week you will demotivate, we will motivate you again. That is there in addition to classes, those things, because this is a GATE training. Here that thing also available, right? If you want to get motivation by yourself, watch previous toppers interviews. If you want self motivation, watch previous toppers interviews from YouTube channels, then you will get good motivation levels. Keep your target first. So work for the target. So some student asked this doubt. So this is about answer for your doubt. Let me complete this machine. So whenever we are moving left side by making this B as Y, all number of, see here, all number of Y's replace, all number of A's also replace. So A's we have to replace, move left side, Y's also we have to replace, move left side. It is a systematic one. What is the logic here? A computer program, algorithm, everything is systematic one, step by step, normal systematic thing. If we are able to make this, if we are able to construct like this, then our program, or we can run that program on the computer, the problem becomes solvable. So our logic is nothing but we are trying to make the machine in a systematic way to solve our problem or to accept our strings here, because these are languages. Right. Then again move until all bypass all this, X come to this state. Again same concept, A comes, make it as X. After that Y's bypass by replacing same, B's make it as Y. After that move left, any number of Y's bypass, x comes, we are in this state now, q0 x comes, will come here. From q2, whenever x comes, replace it by x q0. Now what happened? From q0, yeah, somebody asking the doubt, is it possible for everyone that can prepare for GATE with job? Yeah, obviously. Do your job in the daytime, evening time, early morning time. Early morning, 5 to 7, 5 to 8, you can do your preparation. Evening time, you can attend your classes. Nowadays, classes are online, recordings available. In a weekend, Saturday, Sunday, you can prepare. That is also enough. Most of the students doing some private jobs, after getting good rank, they are moving to PSUs like ISRO, DRDO, BHEL, NIC. The only thing is you have to manage your time. Generally, what people will do is they will do the job the weekdays, in the weekend they will go for enjoyment. If you utilize that time, weekend time, that is possible. The last 2 months of GATE preparation, like December and January, there you have to carefully have to read. If possible, you can take a leave for 1 month or 15 days. That is possible. If any person is doing job, it is easy to get below 100 rank in GATE if he plan his schedule properly. Right. So now we are in q0 here. From q0 y comes. See here, all the a's are over. Whenever a's are from q0 a's are coming, the machine is moving this side. The machine direction will be this side. But whenever from this a's are over, then from this state we'll get y. Whenever we get y from this state, the meaning is all the a's are completed. All the a's are completed. Whenever a's are completed, then we search for any b's left over or not. That's why what we will do is we'll move to some state here. From this, whenever y comes, replace it by same, move right side, search for all b's converted into y's, because sometimes some b's may be remaining here. If any b's left, b's are more, then what happen? We have to halt the machine in the non-final state. For that reason, bypass all the y's, read all the y's, search for any b's left over or not. From this directly, if you get blank, then the meaning is all b's converted into y's. That is the indication. So from this, whenever you get blank, then we'll move to the final state. QF blank, replace it by blank, right side. So this is the way. Right. So this is the machine. The machine is very easy one. See here the main thing is our logic. Logic is the main concept. If you want to construct any push down automata Turing machine, our main aim is construction of a valid logic. So logic orally I'll explain, we'll do manually roughly. That thing, if you present properly in diagrams notation, that is your Turing machine. That's all. Turing machine is not any difficult thing or anything. Turing machine is nothing but one logic. That logic is there in the diagram format. If you present your logic in the diagram format, that is Turing machine. This is called as transition diagram of Turing machine. Transition diagram representation. So anywhere in this, any confusions, the recording is available for you. You can stop anywhere and you can watch the recording. This is the best Turing machine for the language. A equal to a power n b power n. You can try the same logic, similar logic, not same, similar logic. You can try for the Turing machine of a power n, b power n, c power n language. So this language is not accepted by finite automata, not by push down automata, but Turing machine will accept with a similar logic. Replace, read, replace by other symbol, move left and right. Turing machine will accept this. A power n, b power n, c power n, d power n. Any number of comparisons Turing machine will can handle. So what are the capabilities here? Moving left right, turnaround capability, read write capability. So these are the powerful capabilities of the Turing machine. Turing machine seems to be very simple one, looking like finite automata. It is more powerful. Okay. Any doubts, students, regarding this? So we construct this by your own. First take this example, construct by your own. Take the logic and construct by your own. Wherever you are facing difficulty, watch the recording, then you can understand clearly how to construct. In the coming classes, we'll construct very interesting and more somewhat complicated Turing machines, and then based on that, how we'll decide about decidable problems, undecidable problem. Those things we are going to study on our next class. Okay, so that's all about today's session. We'll see in the next class. Thank you guys. See you all in the coming class. Bye bye. Take care.